And we're back. Welcome back and happy Tuesday. Today we will talk about radial basis function, which is an immensely useful machine learning model. But before we begin, some administrative bits. The reading for radial basis functions is Supplementary Material Chapter 6, specifically Section 6.3. It's in the course resources folder in the course Blackboard site. Homework number 3 is out. It will be due a week and a half from today, Thursday, the 22nd of April. It will be at the usual 11:59 and 59 seconds p.m., 1 second before midnight. Okay. When we last left off, we talked about soft margins. And for these soft margins, we included a slack variable, psi, and we used that to absorb the extra amount for those points that violated the margin. And so we added up these margin violations and included that as an additional term on our objective. And when we solved the primal problem and took the gradient and did our substitution, we got back a dual formulation as depicted, defined in terms of alpha. And the difference in this treatment with margin violations was that we put an upper bound on our alphas. Alpha n is at most c, that constant corresponding to the amount of margin violations that are allowed in the original formulation. And so this solution to the dual problem, which you solve with the quadratic programming solver, gives you your alphas, and you use your alphas to calculate your weight vector and also solve for your bias term. And this resulted in two classes of margin. You had margin support vectors, those for which alpha n is less than your constant c. And you had non-margin support vectors, those that violated the margin, those for which alpha n is equal to c. And as long as an input vector, an in-sample point, xn, as long as you violate the margin, you're still considered a support vector, albeit not a clean support vector. So let's jump into the radial basis function. Now, with the radial basis function, it is a method for performing a kind of interpolation, and you can use this to build a hypothesis based on the radial distance between a center point and the point in question. And so essentially what you're doing is you're constructing a value based on a mixture, and these mixtures are defined in terms of the set of in-sample points modulated through a weight vector. And so that weight vector defines the influence, but this mixture is dependent on how close the point of interest is relative to each of the in-sample points. And so this is the radial basis function in particular. And this radial basis function, let's deconstruct this. The radial part pertains to this distance, the norm squared, between our center point for that radial basis, xn, each one of the in-sample points, and that particular value of interest, our free parameter x. Now, this is what the radial basis function looks like. And the radial part corresponds to that difference. And then the basis part corresponds to this decaying exponential. Now, of course, if x is closer to xn, this xn is going to have a greater influence on this weighted sum. And if x is really far away, xn is really far away from x, then the influence for that particular xn is going to be small. And so here we have a set of label instance pairs, xn, yn, in our data set. And each one of these in-sample points xn is going to influence the hypothesis on input point x, h of x, and this is based on this radial distance. So this is a way of noting a type of influence with a capture range. And this parameter gamma then tells you how scrunched in this radial basis is, or how dispersed this radial basis function can be. And so here, each of our in-sample points is going to influence our hypothesis based on this radial distance, and it's the same in all directions, and it decays at the same rate in all directions. And so let's take a look at how you use the radial basis function model for learning. So let's suppose you have your radial basis function definition for h of x. And this can be a real value. The specific real values would be the unknown labels from the target function. Now, in the real valued case, of course, you could find some instantiation of the parameters wn such that this weighted sum of these radial distances relative to each of the in-sample points is going to result in that real value. And so, in essence, what we're trying to do is to find a set of parameters, and you'll notice that there's a weight associated with each of our big N many in-sample points. And so our h of x is defined as our sum for little n goes from 1 to big N, Wn, our weighted interpolation, if you will, of this radial distance modulated by gamma, that distance proportional to the norm between our x input value and each one of our in-sample points, xn. And so this is going to result in a scalar. Now, if we have our data, x1, y1, x2, y2, up to and including xn, yn, for big N many in-sample points, essentially what we want is, given our label instance pairs, is for our in-sample error to be 0. So what does this mean if our in-sample error is 0? It means that our radial basis function h of x is precisely equal to yn given some input xn. And we want that to be the case for every single in-sample points, all big N, many of them. So what exactly does this mean? Well, we'll set this up. It means that if we were to take our weighted sum, evaluate it on xn over all of the radial basis distances over our entire data set for little m goes from 1 to big N, and we're changing the index here to m, we want this weighted sum of each one of these distances between all of our in-sample points xm and our parameter xn, we want that weighted sum to equal precisely yn, the label associated with xn. And so here, if we take this and we do this over the entire data set, we want to do it not just for xn, but for all of the xn's, where n goes from 1 to big N. So what does this give us? Well, here we have one equation, and we're going to repeat this equation n many times for each one of these unknowns, n. So this gives us n equations in n unknowns, where the n unknowns is going to involve each one of these n many w values, these weights. Our n equations corresponds to this equation for xn, where n equals 1, xn, where n equals 2, etc., up to including this equation where xn for n equals big N. So this gives us n equations in n unknowns. So we can actually solve for this set of weight vectors w by expressing our n equations in n unknowns in matrix vector form. And so this is going to give us a coefficient matrix, and we're going to call this coefficient matrix phi. And if we look at this phi, we see in each position, and it's a different phi, not the transformation of feature space. This phi, if we look in each position for this linear system, we see each one of our equations, that's for xn, x1, that's for x2, that's for x big N, for all of our values of xn. And then and you'll see that here. And then for each of the columns, that's for each of our set of equations you see here, this radial basis, right? That represents that sum. Here we have xm for m equals 1, xm for m equals big N. And so each one of these rows is one of our equations where each column is a term in our radial basis model. And so we want to multiply each equation, each row, by a weight vector. So there's our weight vector, W1, W2, up to including W big N. And we want this product of our n equations times our weight vector is equal to our target vector y. So now that we've done this, well, let's think about this. We have n equations in n unknowns. So the rank of phi is going to be n, because that's the number of equations, by n. Because we know that we have n by n, so it's a square matrix. And let's assume that this phi is invertible. So we take our phi, w equals y. We left multiply by phi inverse, both sides of equality. So that's phi inverse. And this goes to identity, so we're left with w is equal to phi inverse times y. And so what does this represent? This represents the mixture w that provides for an exact interpolation of these target labels on each one of our in-sample points. And this interpolation is defined by an influence w relative to the centers of our radial basis functions, which is each one of these in-sample points. So it's saying what mixture of our in-sample points through these bases are equal to or explains the output of the hypothesis. So you can think of these weight vectors as a type of influence. All right. So let's look a little bit at this gamma. Now, we defined not just the radial distance between our input to our hypothesis and each one of our in-sample points, xn, we also had this gamma. And this gamma, in effect, can increase or decrease the capture range. And so what happens if our gamma is small? If our gamma is small, we end up widening the capture range for this negative exponential. If gamma is large, well, that's a bigger negative exponent, and we end up narrowing the capture range of this radial basis. And so if the capture range is more broad, in the case of small gamma, we're going to have an influence on a value that is further away in feature space. And so here on the right-hand side, we have a small gamma, and we have 3 points here, here, and here. They're one-dimensional. And we put a radial basis function kernel over each point, centered at each xn. And so here's one of them. Here's another one, second one, and here's the third one. Now you notice here, these are more dispersed. Their capture range, or their deviation, is much larger. And so when we add them together through weighted combination, we get this smooth curve, and we note that this smooth curve passes through each one of these points. And so this is a really nice smooth interpolation. But what happens then if we use that radial basis function with a larger gamma? That means we're going to be more peaked around each input value, 2, 3, and it's not going to be as smooth. You notice that we have these gaps here between our points. And so the impact of this gamma is an increased semblance of smoothness in our radial basis function solution. So let's take a look at using a radial basis function for classification. Now, of course, when we used phi inverse, that is for real valued predictions based on a smooth interpolation over our in-sample points. But what would we do for classification? Now, of course, we have our form of a classifier. We have our radial basis function, and that gives us a real value, and we call this our signal. And of course, like we did in classification where it was just W transpose X, we take our signal and then we pass that into the sign function to output a +1 or a -1. And so to solve the radial basis function model as a classifier, we go back to exactly what we did with regression to bootstrap perceptron learning algorithm. And so when we did linear regression for classification, we took our score and then we minimized the square error loss between our score, treating the +1, -1 label as a score. We minimized the squared error loss between our +1, -1 label treated as a real value and the score on our data set. And then once we got that particular regression solution, our set of weights that solved this problem of squared error loss, we then wrap sign over that score using that set of weight vectors, and this is now our hypothesis. So in similar fashion, we solve the regression problem treating our +1, -1 labels as real values. And then the solution of that regression problem wrap in a sign in our hypothesis as our solution for classification. So we will end there. Today is a short one, and we'll pick back up on Thursday. As usual, please stay healthy, stay safe, and I'll see you Thursday.